That's for the general example. Now, let us see how the generating function behaves in the recurrence relations. So, we represent a generating function as gz. Z is the any variable. Gz is equal to, we represent sigma n varies from 0 to infinity fn into z raised to the power n. That is equal to f0 plus f1z plus f2 z square plus f3 z cube plus so on. Here we have considered n greater than or equal to 0. This variation is the very important in the generating function. Here over n varies from 0 to n. 0 to n. So it is a general form of a generating functions. Now, first we will see how we can generate the generating function. Then we will see the solution by using the generating functions of the recurrence relations. Now, first of all, we see the generation of the Fibonacci numbers by the generating functions. See, find the generating function. Find the generating function for sequence fn where n is greater than or equal to 2. It means fn is equal to fn minus 1 plus fn minus 2 with conditions f0 is equal to 0 and f1 is equal to 1. We know it is a standard Fibonacci sequence. First of all, we are going to find the generating function for any sequence. Say the given sequence is, it is the Fibonacci numbers. That is, we consider it as number 1. Solution. There are the fixed steps for each problem. First of all, we write fn is equal to fn minus 1 plus fn minus 2. We take it here number 1. Then write the generating function gz is equal to sigma n varies from 0 to infinity fn zn is equal to f0 plus f1z plus f2z square plus f3 z cube plus so on. And we say it is number 2. Multiply both sides of 1 by z raised to the power n. Always we multiply both sides of the 1 by z raised to the power n. Then what we get? It is fn into z raised to the power n. fn minus 1 into z raised to the power n plus fn minus 2 into z raised to the power n. Take it number 3. After that, we consider the given values of fn. Here, which are the given values of n? So, for that, it is the most important point for this recurrence relation. N is greater than or equal to 2. But for the generating function, we consider from 0 to infinity. here n is greater than or equal to 2. When we put n is equal to 2, 3, 4 and so on in 3 and sum up, put the values of n, 2, then 3, then 4 in the vertical form and then sum up all the terms. Why we have taken from 2? Because in this sequence the value of n is greater than or equal to 2. We are concerned with this situation of the n. If we sum up means sigma. We can write sigma n varies from 2 to infinity. It is fn z raised to the power n is equal to sigma n varies from 2 to infinity fn minus 1 z raised to the power n plus sigma n varies from 2 to infinity fn minus 2 into z raised to the power n. The first term, it will start from 2, 3, 4, 5 and then we sum up all this. We get this situation, this step. Now we take it, say, number 4. So we can calculate this whole relation simultaneously, or we can calculate each term separately, then putting in number 4 or by summing up. So we take first term sigma n varies from 2 to infinity fn z. What does it mean? Let us see here. The variation of n is from 2 to infinity. We start putting the value of 2. That will give f2 z square in this function. N is equal to 2. Summation means plus. Then n is equal to 3. f3 z cube plus so on. Yes, we discussed previously. Each term is itself a sequence. Each term itself is a sequence. No, we compare this with the generating function here in number 2. What is the difference? We see it starts from f0, f1z, then this. But this expansion shows f2 z square. If we reverse the values, it means from 2. We see we keep these values on the right hand side and we transfer these both values on the left hand side. We get that is equal to gz minus f0 minus f1z. It means this term is equal to this gz. How? It is the generating function, but the first term of the reconciliation, it starts from f2 z square. It means from here. Then what we do? We transfer the previous terms to the left hand side, that is the gz, so that this bracket is equal to this. Then similarly we can find second term, that is sigma n varies from 2 to infinity fn minus 1 into z raised to the power n. It's a very important point. Again I repeat, it is the variation from 2 to infinity, because it is the restriction of the n in the sequence. But in the generating function, it is always the variation from 0 to infinity. Add this difference, and value of, it means value of n, and this, it will generate the reference relation for the generating function. If we start putting value from the 2, here we get f1 z square. If we put 2 here, f1 z square plus f2 z cube plus so on. Then again we compare the right hand side with the right hand side of the generating function. Here f1 z square, but it contains f1 z. f2 z square, it contains f2 z cube. So we can take z as the common. f1 z plus f2 z square plus so on. No. This bracket we compare with the given value of the generating function. It starts from f1z. It means from, if we delete this sequence from the right side, what we get, that is gz minus z into gz minus f0. That's so we are using generating function at every step. Now what's about the third term? We see it is sigma n varies from 2 to infinity f n minus 2 into z raised to the power n. Now we start putting the values for n. If we put n is equal to 2 here, we will get f0 z square, then 3 f1 z cube plus so on. Again compare this bracket with the given generating function. We see f0 is alone, f1 z and here f1 z cube. So we take z square common, f0 plus f1 z plus so on. And we see this bracket, it starts from here, and the whole right hand side, that is equal to gz, that is z square into gz. Gz, it is a generating function. Now we compile all the values according to the condition 4. From 4, what we get, this is equal to gz minus f0 minus f1 z is equal to this term is equal to z into gz minus f0 plus this is plus z square into gz. That by using the generating function, we converted the function into this. Here, for the further solution, we are depend upon the given values. f0 is equal to 0 and f1 is equal to 1. It means gz minus, what is f0? That is 0 minus, what is f1? 1 minus z is equal to z into gz minus 0 plus z square into g. Substitute the given initial value conditions. It means we see gz minus z is equal to gz plus z square into gz. That is gz, we compile on the same sides, minus z, gz minus z square gz is equal to z. From left side we can take common gz and it will give 1 minus z square is equal to z. It means Gz is equal to Z upon 1 minus Z minus Z square. It's a very important example as concerned with the generating functions. Previous to this, we discussed only a general example in our daily life. It is the generating function for the Fibonacci sequence or the Fibonacci numbers. In this way, we can find the generating function for any given relation. We add the further steps. For that we take some other example, how to solve the given recurrence relation. If we proceed further, we can solve this generating function for the given reference relation. That is, in this way,